Alright, so in the previous video, we introduced this idea. Alright, so in the preceding video, touched on the idea of we want to find the area under a function. Right? We want to find the accumulated area of a region bounded by a function, the x-axis, and some starting point and stopping point. And what this is going to lead us to is the second fundamental problem that calculus was derived to solve, which is going to lead us to this big theorem called the fundamental theorem of calculus. Alright, so I'm going to look at another example. Alright, it's a marketing type example, and we're going to set up and again talk about area. Alright, so we've got this market research that we've done. Alright, so we've gone to an electric store, or we've estimated an electric store based on past research or something. So we've collected some statistical data, right, either past or present. Alright, so we calculated that the rate of sales of a new phone T days after it's been put on the market is the following. Alright, so we're basing this on, again, like I said, some type of statistical information. So either we've observed it or it's based on some type of modeling. We assume over the first day, which is time 0, the rate of sales will be 60 phones per day. 10 days later, it'll be 45. 20 days later, 32. Up to 50 days later, it'll be down to 18 phones per day. That's the rate. They're not selling 18 phones. That's how fast they're selling the phones. Remember, that's the speed at which the phones are selling on that 50th day. All right, and so I graphed the points, and so that's what, if you've got your handouts there, that's what this graph is these are my points. The y is the rate of sales, right? That's the y value, the x value, which is my number of days. And so those are my points, all right? So I've graphed them here. So this would be the first point, 0, 60, 10, 45, 20, 32, and so on. And so I'm going to draw a dotted line and connect my points. Alright, so there are my dots, and I've collected over the first 50 days. Alright, so I've graphed those points. If I find the area here, alright, the area under this set of information, alright, what that area will find is it will find, based on the rate of sales over each 10-day increment, and again, it is an estimation, so it's a big-time estimation based on our limited statistical data. All right, but based on our limited statistical data, if I can spit it out, can give me a pretty good approximation of how many phones they would expect to sell. That's what this is. This would give me the total sales for our cell phones over the 50-day period. All right, that's what that area represents. All right, based on my 10-day increments of my speed of sales, rate of sales. All right, so we want to find that area. Well, the problem with it, again, is there's no direct way to do it. All right, and there isn't unless I find a function that models it. So what I can do is I can use my information that I've given, and I can draw areas, again, I know how to find, right? Just like we did with the derivative, right? I couldn't find the instant rate of change directly because I ran into the 0 over 0 problem. And so we went back to average rates of change and found the limit of those average rates of change. I could find an average as it approached my instantaneous, right? As my change in value approached 0. Right? Same thing's going to be done here in terms of area. I can't find this area directly, but what I can do, well, I can go back to something I know how to find. All right, how can I find the area? Well, I can find area of rectangles, right? And so what I can do is I can split this picture up into a bunch of little rectangles, and so that's what I'm going to do. Now the problem is there's two ways I can draw my rectangles between my points, right? I've got these 6 points here, and there are two ways to draw my rectangles based on those points. There's a right-sided area that I can find, or a left-sided area. There are actually other infinitely many ones that we can draw, but like I said, in this class we're going to keep it fairly basic. So we're only going to look at the two cases. We're going to look at the left side and the right side because those are the two easy cases. All right, so those are the only two values I'm going to find. All right, so right side or left side. Right. If I go back to my original picture to kind of draw out what I mean, is I can draw a rectangle starting on the left, and I can draw them like this. Right, going back to my rectangles. Or, so it would be the left-sided, I can start on my right. So this would start on the left. I'd start at 0. Or I can start on the right. If I start on the right, I start at 50. All right, and I draw my rectangles. All right, and so I can find either left side. So they aren't perfect, right? My right side and my left sided are going to be bigger or smaller, and the actual area is somewhere in between. All right, either halfway in between or somewhere in between. All right, and so that's what we're going to do. There's two ways to draw my rectangles, and I'm going to draw both of them. All right, so I'm going to draw both from the left and the right. So I'm going to start out with my right side. And so what I mean by my right side is if I have my point, I'm going to write my points because I actually need to know my point value. So this point was the first value, 0, 60. This was 10, 45. This one was 20, 32, 30, 28, 40, 22, and 50, 18, right? And so the y values are my rates of change, right? In phones per day. The x value is my time, right? And if you'll notice, the change in time between each point is 10, right? The delta x means change, right? Between each of my values, there's 10 units between each of them, right? They're drawn at 10-minute increments. And that's where I'm going to draw my rectangles. I'm going to draw them over each of those 10-minute increments using my points. Now I'm going to start on the right side. All right, this is the right-hand Riemann sum. Meaning I'm going to draw my rectangles from the right. Meaning to the right, I'm going to start at 50. 50 is where I'm starting. All right, on the right side. And so I draw my rectangle using the 50 as my height. All right, and then the next one starts at 40, 30, 20, and then 10. And there are my rectangles. All right, so again, the heights that I'm using for each of these, if I draw my rectangles, come from the right side of my rectangle, right? This would be the right side of my rectangle. The width of each rectangle is that 10, right? Right, that change in x. The width of each one of these is 10 units. All right, and that's by design. All right, I wanted them to be evenly spread apart, and so that's by design. And so what we're going to do is we're going to approximate area. We're going to estimate area using those 5 rectangles, taking area 1, adding it to area 2, area 3, area 4, area 5. Right, there are 5 rectangles. Right, which I can find those. They're rectangles, right? I have an equation that finds area of rectangles, which is width times height. Well, the width of each of them is 10. The height comes from the y value of my function, right, using the right endpoints. And so these are the right values that I'm using. Right, those are the ones that I'm using in order to find my height. So on my first area here, it's on the right side of this, and so this is the height. Well, that height is that 45, right? 45 is the height of that rectangle, all right? On the second rectangle, this is the right side of it. I use that height. Well, that height is 32. All right, the third one, that height is 28. The fourth one, that height is 22. And the last one, that height is 18, right? I'm using my rate of change values, right? The y values. That's the height of each of my rectangles. And so when I find those, I'm going to take my area of my first one. Well, my first one is 10 times, right? The area of rectangle 1 is 10 times 45. Well, that's 450. Right, the next rectangle is 10 times 32, 320. The next one is 10 times 28, 280. And the last rectangle, oh, not the last one, skipped 4, and then 5. The fourth rectangle is 10 times 22, so 220. And then the last one, 10 times 18, which is 180. So again, I'm adding up these areas. So this area was 450, this area was 320, this area was 280, 220, and 118. All right, if I add them up, that'll estimate my approximate area. So again, if I add those together, it comes out to 1,450 is my estimated area. Now, if I go look at my picture, I connect my dots, right, this would be what we'd call a low estimate, right? My actual area should be bigger than this. So this would be a low estimate, right? Because I'm missing these areas here. All right, there's some area above each of my rectangles that I'm missing out on. But at the very least, I know that the actual area should be just a little bit bigger than 1,450. All right, I'm going to do the same thing, but using my left-hand rectangles. All right, so I'm going to draw rectangles now from the left end points versus the right. All right, so now I'm going to estimate using what's called the left-hand Riemann sum. All right, so remember, I'm going to write down my points so that you can see them here. Right, so the width is still 10, right? The distance between each of them is 10. That's that change in x. But now I'm going to use the left side. So it means I'm starting over here, right? The left hand, what's called the Riemann sum. All right, so I'm going to use the left side. So I'm going to start at 0. 0 is at the leftmost point. And so if I use this value is going to be on the left side. I can draw a straight line. So this is the side of my rectangle, and I hit my point, and then I draw my first rectangle using that side. All right, then the next one starts at 10, then at 20, 30, and then the last one is at 40. All right, and so those would be, so I've got 5 rectangles again. This is my first one, this is my second, third, fourth, and fifth. All right, and so if I'm using my left side, I didn't really give myself enough room to write it down, so I'm going to give myself a little space here before we talk about that. All right, so sorry about that. All right, so giving myself some space to find my estimated area. All right, so area is estimated, approximated by adding up those 5 rectangles. All right, and so using the left side, all right, so now I'm using the left side versus right. So the left side means I'm going to start here on the left. So this first rectangle now has a height on the left side of 60, right? It goes up here, and that's its height at 60. The next rectangle starts at 10, and its side's on the left here, which is my 45. The next one's here at 20. Its side goes up to 32. 30, its side goes up to 28. 40, it goes up to that point, which is 22. And then we stop, so we don't use the last point. So the points we're going to use are 0, 10, 20, 30, and 40. All right, and those are the areas we're going to find. So the area of the first rectangle, these are still 10 between each of them. All right, the area of the first one is 10 times 60, which is 600. Next one is 10 times 45, 4,500. Next one is 32, 280, and 22. And see, these last 4 are actually the same as the first 4 of the previous example, right? What I don't have is this 180. I'm interchanging this 180, which was the rightmost rectangle, with this leftmost rectangle, which is 600. And so when I go to find my area now, it's the 600 plus the 45, that's 450, not 45, 450, 320, 280, and 220. All right, and so I add up those values, and again, this is going to give me an approximate area. When I add them up, it adds up to 1,870, which is my estimated area. Now, if I connect the dots, you'll notice that this area is above, right? I've got these pieces that land above my dotted line, and so this would be a high estimate. The actual area should be lower than this. All right, so I have a high estimate and a low estimate, and so that's my next statement. All right, so I know that the area is less than 1,870. I know it's bigger than the 1,450. And so the actual area, which represents the amount of cell phones they would expect to sell over the first 50 days, is between those two values. My area should be less than 1,870, greater than 1,450. So again, if I were just using this that we found, my left, this would be my left, this would be my right hand sum. So if I was just using that information, I know that based on my research and the rates of change, over the first 50 days the phone is on the market, we should sell between 1,870 and 1,450. All right, that's what the sales number should be between. And a lot of times what they'll do is they'll average the two. All right, they'll take the high value, the low value, and average them. So if we average the two, all right, we add them up, divide by 2, probably a more accurate answer. And again, it wouldn't be exact, it's still an approximation, it's still an estimation. Based on my research, they would expect to sell around 1,660 cell phones. The area should be close to that value, all right, based on the information I've collected, the statistical information. All right, and so that's an example. We're going to do more of those examples later on, because again, these are the ones where you kind of have to use this method in order to do this. But the theory we're going to get to in the general case, and so that'll be the next one. We're going to then look at in general for functions instead of just giving tables of values and doing like those cases. This next example is going to be in general. And so that'll be my next video. My next video is going to pick up the in general case, where the theory is going to lead us to special type of limit, just like the derivative was a special type of limit. Finding the accumulated sum of a function is also a special type of limit. All right, and that'll be the next section.